Everybody, welcome back. Mr. Smith here. In the last slide deck, we introduced the statistics of radioactive decay. And what we did was just based on a few facts like the lambda constant and how much of that stuff you had, you could figure out what are the chances of it emitting radiation. So how hot was it? The thing that we didn't do was we didn't account for the fact that if a radioactive isotope is emitting particles, it's actually changing. So it's changing into something else that's not as radioactive maybe. So what we're going to do in this slide deck is to take the equations that we developed last time, these first two, and we're going to evolve those into these other two equations, equations 3 and 4, that are going to let us study radioactivity as a function of time. And so before I get into that, what I want to do is take a sidestep and go back to some math that you should know. So what you see here are a lot of the basic rules of logs. So I'm not going to go through them all, but I just trust that you could take a look at them and remember them. You're going to see me do the following thing. I'm going to talk about the fact that the natural log is partnered with the base e in calculus. And so if I were to have something like a function e to the x, and I decided I needed to take the natural log of it, what's going to happen is I'm going to use rule number 3 here, log of m to the k. So what I do is just take the exponent, pop it down, and I get x ln of e. And then I remember the fact that natural log and base e are partners. So I'm down at this 5th step right here, where if I take the log of the base, I just get 1. So really all this thing right here, x ln of e, just turns into x. Okay? So you're going to see me do that step and a couple more. What I want to do right now is launch into a calculus derivation of where our dynamic formulas come from. Feel free to ask questions about this as we get into class, but what I'll do is I'll just walk you through it and you'll see me do some of the log steps that I wanted you to see. So to begin with, delta n is the number of nuclei that pop or change per unit of time. What I'm going to do is turn those into differentials. So really nothing changes except that I make in my mind the number, the amount of time very small, and probably the number of n's that are popping small. So what happens as a function of time is that the dn by dt is going to change and it's going to lose nuclei. So the change over time to the number of nuclei is actually going to be a negative function of lambda and the number of nuclei I have. Okay, so that makes it dynamic. So what I'm going to do is just a little algebra. Let's go ahead and move the dt over and move the n under, and I get dn over n is equal to negative lambda dt. And so nothing fancy so far. This in calculus is super well known. If I ever need to integrate this, what it's going to always turn into is the natural log. So I'm going to make a definite integral out of this. So I'm going to put limits on it. And so I'm going to integrate from n0, the number of nuclei that I have at the beginning of time, to n, the number of nuclei that are left at moment t. So I'm going to integrate that, dn over n, and that's going to equal negative lambda. And that's a constant, so I can pull it out in front of the integral. And I'm going to integrate this from t equals 0 to our moment t, and just dt. So as integrals go, this is one of the easiest things you'll ever see. What I end up getting is the integral of this whole thing, is I'll put my limit bars on it, from n0 to n of the natural log of n equals negative lambda, and when you integrate dt, you just get t, so I'll put 0 to t of the letter t. And the way I do, if you haven't seen it before, the way I evaluate definite integrals, I'll pop down here. I just pop in the top limit and subtract the lower limit. So the left-hand side of this equation becomes ln of n minus ln of n0 equals, and do the same thing over here, negative lambda times, and I pop t in for t, and that's ridiculously simple, and I'll pop 0 in for t, and you can see what happens there. Anyway, so long story short, by pulling a couple of levers with the natural log, what I end up with is ln of n divided by n0 equals negative lambda t. So I'm going to take one more slide and just finish this thing up. What I want to do is unimprison n and n0 from inside the log function. And the way I do that is by using the exponential. So I'm going to raise e and use this now as a power, and I do it to both sides because we're doing legal math. So I raise all of this nonsense to the e power. And what happens is, because log and base e are opposites, what I get is simply n over n0 on this side equals e to the negative n, or rather negative lambda t. And then so here you can see where I derived my function from. So this leads me to n is the number of nuclei left in a sample at a given time, equals n0, the number of nuclei you start with, e to the minus lambda t. So that's the derivation. What I want to do is just zip back and talk real quick about the fourth formula. Same idea. This is the activity of a sample. The activity of a sample starts out with a baseline activity. So at moment 0, you have a certain number of counts per second. And that activity will also decay like a function of e to the negative lambda t. Okay, so that's how the whole thing works. That's how we made it dynamic. So let's go and work a couple of examples and to see that's not bad at all actually in practice if you just remember the log rules. Okay, so let's get to it. So in our first example, we have cesium-124, has a real short half-life, so it's going to be very radioactive. And we start out with 8.24 micrograms, and they want to know how many nuclei. Okay, so I already worked that out because you should know how to do that from the last slide deck. We just do 1 mole over 1 mole of cesium-124, and we get 4 times 10 to the 16 nuclei in our sample. Okay, so that should be easy. Second thing we're going to do is I want to be sensitive as I use these formulas to units that make sense. So if they say how many nuclei are present 2 minutes later, and they give me the half-life in seconds, it's pretty useful for me to get the lambda in terms of seconds, because this isn't going to be very hard for me to work with. Well, it might make sense if they had a number of years here that I wouldn't want to use seconds for my lambda. So you'll see what I mean. So lambda equals 0.693 over t1/2. I just laid that all out. And I got the lambda for the sample. Okay, so what are we going to do to get b? It's actually really easy. To figure out the number of nuclei that are left, it's just going to be n is the number of nuclei we started out with at the beginning of time, e to the negative lambda t, and just make sure you're careful with labels. So this is going to be 4 times 10 to the 16 nuclei, e raised to the negative, and now I go lambda t, right? So 0.0225 seconds to the minus 1 times, in my exponential, 2 minutes. So that's got to be rewritten in seconds. See what I mean? So it's really important to pay attention to the labels. You're in the power of an exponent, and you cannot have labels left over in the power of an exponent. Anyway, plug that into your calculator, and what you should get is 2.69 times 10 to the 15 nuclei remain. And you can get then the number of nuclei at any moment in time that you want. Okay? By the way, check it out. With a half-life of about 30 seconds, this is about 4 half-lives, right? So see if this makes common sense to you. Did we divide this number in half, and then half, and then half, and then half again correctly? Yeah, we should have gotten about 0.25, right? Where we started out with 4. Okay, moving on. Let's go check out C. So what's the activity of the sample after 2 minutes? Okay, that's the fourth formula, right? We're just going to use this one. Delta N over delta T is the activity of the sample right now. And that equals the activity of the sample when we started. So the 0 version of that also times my decaying exponential function. So what I need to do really in this problem is just get this one, right? So I know that delta N over delta T when time begins is equal to lambda times n. So I'm just going to go ahead and pop those in. That's going to be lambda was 0.0225 seconds to the minus 1. N was 4 times 10 to the 16 nuclei. And we get we get 9 times 10 to the 14 nuclei per second was the decay rate at the very beginning. And so same thing you just saw me do a second ago. The decay rate now is going to be the same thing we just had, 9 times 10 to the 14 counts per second, let's call it, because it's easier to write, times e to the negative 0.0225 seconds to the minus 1 times 120 seconds And they made this easy by reusing the time, didn't they? And you end up with 6.05 times 10 to the 13 decays per second. And that's what happens, as over time the activity of a radioactive sample will decline just as the nuclei are. Okay? And finally, what we're going to do is use a little bit of log skill here. At what time will the activity of the sample drop to 1 per second? So it's the same exact formula as the one we just did, but let's write down, instead of delta n over delta t, let's write down 1, because that's what it was. So delta n over delta t equals the original delta n over delta t, and that was 9 times 10 to the 14 times our exponential. And what we're going to need to do then is to use some log stuff to get into these right here and ultimately figure out t. So what I'll do is just get about that. I'll take the ln of 1, and I'm going to then take the ln of everything over here, and I'm going to use a little bit of smarts because I know that the ln of this product is equal to the ln of 9 times 10 to the 14 plus the ln of this exponential. So e to the negative 0.0225 times t. And so what I do is evaluate where I can. So I'll simplify it. Natural log of 1 is the same as any log of 1. It equals 0. Natural log of this number equals 34, I wrote it down, 34.43, yep. Plus, because base e is the natural log base, what that does is liberates all this stuff. And I get plus a negative 0.0225 times t. So really it becomes a very simple algebra equation to solve for the time, as long as you know a little bit of log rules. So just simplifying, I'll swing the 0.0225 t over to the left-hand side equals 34.43. And we just divide both sides by 0.0225, and we get t equals 1530. Really important. You've got to pay attention to the labels, right? This was seconds to the minus 1, so because of that, we're obligated to write down seconds for our time. That's what it is. So 1530 seconds. So about 50 half-lives, right, before this sample is good and dead. Okay? Anyway, you might have some questions. Bring them with you if you do. But looking forward to seeing you in class. Take care. Have a great day. Bye-bye.